Okay, and the final example of this set, we're looking at problem number 12-105, and the problem says a boy at A, and I guess the boy got chopped off, attempts to throw a ball over the roof of a barn with an initial speed of VA is 15 meters per second. Determine the angle theta A at which the ball must be thrown so that it reaches its maximum height at point C at the top of the barn. Also find the distance D where the boy should stand so that he makes the throw. Okay, this one is a peak of flight or an upper limit on the flight, and so we recognize that kind of problem as a vertical velocity equals 0 at the peak point in the flight path. And so we also see that we have, let's go ahead and sort of diagnose this one. Two-state problem, clearly. There's a state number 0 and a state number 1. State number 0 is at point A, and state number 1 is at point C. And at point A, we know that the speed, magnitude of the velocity, is equal to 15 meters per second. That was given in the problem statement. And we can choose to say that, and we need to make some choice on origin. I'm thinking we'll probably put the origin right there at the bottom, so that at that point x equals 0, and at the other point x is equal to unknown, but it's d plus 4 with d unknown. And at the starting point, y equal 1. At the final point, y equal 8. Again, time is not specifically requested. Time probably will come into the problem because the horizontal distance is unknown, and our horizontal distance equation is going to have time in it. So I think we're going to be heading toward time. So I'm going to also say that here time equals 0, and here time equals unknown. Now, one other thing I haven't written down is that at point C, and that's important in this problem, V in the y direction, in the vertical direction, is 0. And the other thing that's true is velocity in the x direction throughout the problem is constant, whatever it happens to be based on speed and angle. And so we would maybe like to deal with what's happening in the vertical direction. And in the vertical direction, we have some velocity information at both points, and we have y information at both points. So it appears to me that we could use an ADS equal VDV equation to learn something, but we also can always use the time-based equation. What I see from the author's solution is he wrote two time-based equations. Let's look at that, and then we'll talk about how the ADS equal VDV would probably change that. So, in the vertical direction, knowing velocity information at both pieces, we can write a time-based equation, which would be, where did my equation sheet go? Here it is. And of course, we're in the constant acceleration section. So constant accelerations, transitions here, A equal constant from 0 to 1. Here are our constant acceleration equations. Let's start off by writing this velocity equation where, since we're working the y direction, A is going to be a minus g value. So, in transitioning from A to C, our final velocity in the y is equal to our initial velocity in the y plus acceleration times time. Our final velocity in the y is 0. Our starting velocity in the y direction is 15 times the sine of theta. The 15 was given. theta unknown. Acceleration of gravity in our metric system is a 9.81 meters per second squared, multiplied by the time to reach point C. And in this problem, we don't know theta A, and we don't know time. So one equation, two unknowns. A reasonable thing then, because we do know some distance information in the y direction, let's write a position equation in the y direction, which would say that S at our final direction, that would be point C, is equal to the y location in our initial position, which would be point A, plus speed in the y times time, plus 1/2 at squared, where a again is going to be minus g. So our final position in the y at point C is 8. Our starting position at point A was y equal 1. 15 sine of theta times time, minus 9.81 over 2 times time squared. And our unknowns in this equation would also be theta A and time, appearing in multiple places. But that's the same two unknowns that we have here. This is a two equation, two unknown problem, completely solvable. And solving the equations by whatever algebra techniques you want will give us a theta A of 51.38 degrees, okay, and a time of 1.195 seconds. And that answers the first part of the question, at what angle must this occur? Now, if we had used in this section ADS equal VdV form of the constant acceleration equation, we would have said a v final squared in the y equal v initial squared plus 2 times acceleration times a change in height quantity. If we had written that, what we would have said was, let's see, I'm going to write it right here. Okay, our vy final is 0 squared is equal to our initial vy is 15 sine of theta, that entire quantity squared, and then the plus 2a delta s term would be a minus 2 times the 9.81 times a height change of 8 minus 1. If we look at this equation, this is a one equation, one unknown problem where the theta is the only unknown. Okay, and so we could then solve for theta directly and get the answer we were looking for and not involve t at all. And we could have declared victory on the first part of the problem. Now, to move to the second part of the problem, we're almost certainly going to need t. So what we would really need to make progress is any two of these three equations, the ADS equal VdV or the two time-based equations. Any two of this pair would have given us the theta value and time. And if we had just started the problem using only this equation and declared victory with theta, then we would have eventually come back and written one of these. We'll see that in just a second. If we look at travel in the x direction, the only reasonable equation that we can write that's going to involve that d quantity is going to be our position equation that says final position equals starting position plus velocity, a velocity term, and an acceleration term, and in the x direction, that acceleration term goes to 0. So we're just left with the shorter version of the equation. And so we can say that the starting x value is equal to the, final x value equals starting x value plus the speed in the x direction times time. Now the speed in the x direction is 15 times the cosine of the angle that we just solved for, 9.363 meters per second. So our final position is d plus 4 in the x direction. Our initial position is 0 in the x direction. Our speed in the x times time. Okay, and if we had written this thing initially and simply had time right there. This would have been a 2-equation, 2 unknown problem if we had never solved for time, which would force us to go write another equation, which would bring us back to having written either one of these equations and solve for time. But since we do have time already, we plug it in. Now this is 1 equation, 1 unknown, and the distance away from the barn is 7.18 meters.